So I want to send the YouTube link to the LMS page so that you guys can copy it to our Telegram page for people to join from there.
Good morning, sir.
Wait.
Please, sir, I want to make a comment
Okay.
concerning the
Well,
iNotes you uploaded on the LMS portal.
okay.
Most of
Concerning what?
the lecture notes you uploaded on the LMS portal,
Okay.
most of them are corrupt and displaying unreadable formats.
Corrupt.
Yes, sir.
Which of the lectures?
The lecture 3 and the lecture 4.
Oh, is it for everybody or for only you?
Well, the ones I downloaded like 2-3 times. They bring it the same thing.
Oh. Please send me a reminder on today. What I will do is that I will make sure I convert it to PDF first before I upload it. I think that will be better.
All right, sir. So where should I
But
send
please
the
send.
reminders?
You can send it in the afternoon or in the evening, but preferably
On
from
what
afternoon.
platform?
Oh, you have my. Okay, don't you have my WhatsApp number? I think you have it on
No,
the
sir.
group on the page.
Okay. I'll do that, sir.
Okay. Thank you for that notification. That is setting. So I have put the YouTube link on the Telegram page. I think people are already joining. I don't think it's necessary. So let's start the class. But before that, let me make some people the co-host. Let me make some. Okay, so come in. You are here. Let me make you a co-host because you have been our regular co-host. So come in. You have been made a co-host. Then Olabode Ayodeji. Let me make you also a co-host. Hope the person is here.
Sir, yes, I'm here, sir.
Okay, let me make you our co-host so that you can control the Zoom if anybody is disturbing us. Okay. Okay. Is for okay, Zoom. Maybe I can share now. Okay. Okay. Four. Okay. Good morning, students. So once again, you are welcome to Physics 103 class. This 103 class. So this will be our fourth lecture. So, and I've put the lecture note on the LMS page, and I've attached a video that can help you. So the video explain most of the things I put in the lecture. Please let us download it and watch the video and read the lecture note so that we can have a proper understanding of the course. So let's start today's class. This morning, we start from where we stopped last week. It and the first law of thermodynamics. It and the first law of thermodynamics. So last week I told us that we have okay, heat and specific heat capacity, where we start at the unit of energy, that is the unit of heat energy or energy generally is joule, and we have another one which is called a calorie. So we have the unit to the joule and another one to the calorie. So 1 calorie is equal to 1.186 joules. So, and this equivalent is what is called a mechanical equivalent of it. We have said this last week, but I just need to start from here this month so that it can flow together. So the equivalent that 1 calorie is equal to 4.186 joules. So it's called a mechanical equivalent of heat. Mechanical equivalent of heat. Then heat capacity. I told us heat capacity is the amount of substance supplied to a substance to change the temperature of that substance by 1 degree Celsius. So that is the amount of energy you needed to raise the temperature of a particular substance or particular sample by 1 degree Celsius. So heat capacity is represented by capital C. So, and if the energy needed to raise the temperature of the sample by this change in temperature is Q, then capital C is equal to energy supply per change in temperature, that is divided by that change in temperature. So that when I cross multiply, I'll have Q is equal to C delta T. Delta T is like change in temperature. In secondary school, they always use C theta. Theta is still fine. It's still fine. Just be consistent with what you are doing. But here in this course, I will be using delta T as our change in temperature. So Q is equal to C delta T. This C is capital C. Heat capacity, not specific heat capacity. You have to take note of that. So, and it is the amount of heat energy you supply to a whole sample of something given to you to raise the temperature of the whole body by 1 degree Celsius. So it's different from a specific heat capacity. So if this equation, if I divide it by what's it called? If I divide it by mass, so it becomes a specific heat capacity. That is C over M, which is the same thing as Q over M delta T. So that's what I have here. If I divide the equation above by the mass of the substance, that is called the quantity we get it's called a specific heat capacity. Specific heat capacity. And it is the energy needed to raise the temperature of a unit mass. You have to pay attention to a unit mass. The other time I was telling you that the mass of the energy needed to raise the temperature of a whole body by 1 degree Celsius, it's what's called a heat capacity. But here is the energy needed to raise the temperature of a unit mass of that sample by 1 degree Celsius. So the unit mass, this one is specifying a particular mass. So that's why they call it specific heat capacity. So that's the difference between the heat capacity and the specific heat capacity. If I divide that equation by mass, I'll have C capital C over M, which will give me small c. So that means to get a specific heat capacity, if I'm given a heat capacity of that substance, I need to divide it by the mass. So that I will have Q over M delta T. If I cross multiply it, the Q is equal to MC delta T, like you have in secondary, that MC theta. So it's still fine. But here, as I said before, I'll be using a delta T. So specific heat capacity is a measure of how thermally insensitive a substance is to the addition of energy. That is the higher the specific heat capacity of a substance, the higher will be the energy needed to supply to it before the temperature can change by 1 degree Celsius. So that's why I said this is a measure of how thermally insensitive a substance is to the addition of energy. I've said it, the higher the C, the more energy must be added to a given mass of that substance to cause a particular temperature change. So we have said that last week. The first two slides have been explained last week. So let's continue. The above equation means that if temperature increases, the energy is positive. That is, Q will be positive, and it flow into the system. It means you added heat to that system. But if it's negative, it means it flows out of the system. This is Q. I'm saying this Q. If you get a positive value, it means energy is added to that system. If it's negative, it means energy flows out of the system. So note this statement. We always say that C is a constant for water, is a constant for this material, is a constant, but C varies with temperature. Though they might not tell you this one in secondary school, but in recent, the specific heat capacity varies with temperature. That is, when temperature increases, it varies. However, for small temperature interval, the variation is small, so and can be neglected. That's why they do normally say C varies with temperature. They always say C is a constant because the variation is very small, so they always neglect it. They always neglect the variation. So, for example, for change in temperature of water from 0 degree to 100 degrees, the variation is only about 1%. You can see that if you heat water from 0 to 100, so look at the change in temperature, like 100 degree, they say C will only varies about 1% of the value they call it. So that's 1% is insignificant compared to the real value of the specific heat capacity of water. So they neglect it. So when the variation cannot be sorry, what I will do, maybe I will give you the link to the YouTube link so that you can download the lecture there and listen to it again. Sorry, don't send the request again to record, please, so that you don't distract me. I don't distract other people. So when the variation cannot be neglected, that is, we said when the temperature increases, C also increases or C also changes. And for some substance, that variation is very small, so it's neglected. But when the variation cannot be neglected, so we apply this formula. So when that variation cannot be is significant, so that we cannot neglect it, we use this formula. This formula, that is Q is equal to integral of C dt from initial temperature to final temperature. This is like temperature change, Tf minus Ti. But when you have a change that cannot be neglected, so we can integrate C, the specific heat capacity, with respect to temperature between the initial and the final temperature, multiply that. You will see that this formula is almost the same as this we have here. This is MC and same temperature. But there now, we are not using delta T. The change is very small, but we cannot neglect it. So we can use this mathematical formula that is integral to solve that. They will just give us C in terms of temperature. So we need to integrate it between the two temperature given to us. And I believe we understand that. Conservation of energy. So we say Q cold is equal to minus Q hot. That is it. So the energy lost by hot body is the same thing as energy gained or energy absorbed by cold body, provided there's no energy loss to the surroundings. So, but in most cases, this law is valid. That is, the energy released or the energy lost by hot body is equal to energy absorbed by the cold body. So I use this one for cold body, MC delta T. But this C is telling us is for cold, while this H is telling us that is for hot body. So the initial temperatures of the cold and hot substances are T1 and T2. And when in contact reach a final temperature TF. That is when they are the two bodies are in contact, the mixture or the combination reach the final temperature TF. We call it final temperature TF. Then we have this, so that the change in temperature is T final minus T initial. Here also T final minus T initial. You will see that this is a little bit different from what you did in secondary school. They just say MC theta for cold body is equal to MC theta for. But to show that the hot body is losing energy, is losing heat, that's why you put minus. And if you do it, you will see arrive at the same thing that you know before. So this minus is just telling us that this hot body is losing energy to colder body. So latent heat. So there are some situations in which you will be adding heat. You'll be eating something and the temperature will not change. So though many of us are familiar with this right from our secondary school. Yeah, there are situations in which we'll be supplying heat to a substance, and that heat you are supplying will not result into change in temperature. The temperature will just remain the same. Although you are eating it, you are supplying it, but temperature remains the same. This kind of heat is what is called a latent heat. It's like latent means hidden, something that's hidden. So that's why they call it latent. And it happens or it occurs when phase changes occur. When phase changes occur, that is when that substance want to move from one state to another state, from one phase to another phase. Probably you are eating solid now. You are eating solid. The temperature begin to increase. It will get to the point that as you are eating, the temperature will stop increasing. It will not increase again. It means the heat you are supplying at that time, that substance is using it to change to another form, to transform from solid into liquid, or to whichever state it will transform to. So it occurs when phase changes occur. So there are two common phase changes. We have change between solid and liquid. We have change between liquid and gas. The change between solid and liquid are in two ways. Something can change from solid to liquid, something can change from liquid to solid. So this like a combination of two. The other one is also like a combination of two. So if a substance changes from solid to liquid, that's called a melting. That's called melting. So this like SS1 something. So when it changes from liquid to solid, the process is called freezing. So when liquid change to gas, that's vaporization. When gas change to liquid, that's condensation. We all know this before. And if you don't know it before, it's not a crime, but this is another opportunity for you to know it. So if I bring out a ice block from my fridge and I begin to eat it, it will get a point that the ice block will dissolve and become liquid water. So that process is called melting. The temperature at which that thing occurs is called melting point. So the other way around, when you put your water in your fridge, it will get a point that that water will become solidified. That is, it will turn to solid. So that process is called freezing. The temperature at which that occurs is called a freezing point, and it's the same value with this one. That's why they will tell you the melting point of water is what? Is zero. What the freezing point of water is zero. So take note of that. Then when liquid change to gas, that's called vaporization. That as you are as you continue to eat your water, it will get to one that you will seeing a steam going up. It means your water is being converted into vapor. So that's what they call it, vaporization. So that's why they say steam. The steam is coming out. Yeah, that's vaporization. Then when gas change to liquid, that's condensation. The process by which a substance change from gaseous state to liquid state is what's called a condensation. So other change is between solid and gas. Yeah, there are some substances that when you are eating them, if they are solid, instead of them to change to liquid, they will change directly to gas. They will not pass through liquid state. So that process is what's called sublimation. Sublimation, when solids change to gas, that process is called sublimation. So, and these are the one I highlighted with red ink are the substances that can undergo sublimation. That is when you take a solid hydrogen and you are eating it, instead of you to see liquid before gas, you will not see it. The thing will just disappear to gas. And camphor, ammonium chloride, naphthalene, and so on. Then when gas changes to solid, this is like opposite of sublimation, that we call it the sublimation or deposition. So there's some gases that when you condense them, instead of them to change to liquid before solid, or when you reduce temperature, they will change directly to solid, and that's what's called deposition or the sublimation. So note, the amount of energy transferred during a phase change is dependent on mass. That is, when a phase change wants to occur, the amount of energy you will supply depends on the mass of that. If the mass of that is high, you will need to supply high energy. But if the mass is small, you need to supply small energy before the phase change will occur. That's the meaning of that statement. The energy transfer per unit mass during a phase change is called the latent heat. That is, that latent heat is energy transferred per unit mass. That is Q over M. I use L to represent the latent heat. So latent heat is energy supplied divided by the mass of that substance. So if I cross multiply, I will have Q is equal to ml. So latent heat can be calculated using mass times the latent heat of that thing. But L here depends on the nature of phase change. Yeah, if the something change from solid to liquid, that's latent heat of fusion. That's fermenting. So latent heat of fusion. But if the substance change from liquid to gas, that would be latent. Don't forget that I said when liquid changes to gas, we call it a vaporization. So in this case, we have latent heat of vaporization. That's for boiling. Then let's look at this simple example. Calculate the total amount of energy that must be added to change 1 gram of ice at minus 30 degrees Celsius to steam at 120 degrees Celsius, as shown in the figure below. Okay. So this is figure. The ice, the mass of the ice is 1 kg, 1 gram. So, and it was at minus 30 degrees around this place. Then you begin to supply it. The temperature begin to increase, you will see that this temperature is lower than the melting point of ice. So first thing, when you are supplying it, the temperature must increase until 0. That 0 is here. So in stage A, the temperature increases until it reaches 0. Then when it gets to 0, you are still supplying it. Instead of that temperature to be increasing, to be going up, no, the temperature remains constant. That means all the heat we are supplying here, the ice is using it to change to liquid water at 0. So when the ice has been changed to liquid water now, you are still supplying it to, the temperature begins to increase from 0 until it reaches 100. At 100, don't forget the water we want to change to gas. The liquid water we want to change to gas. So you are still supplying it. On getting to 100, the temperature is not going up again. The temperature is not increasing again. Instead of increasing, the temperature remain constant, meaning that the heat you are supplying around this, that is at stage D, the liquid water is using it to change to vapor, to change to steam. So when all the liquid water has been converted to steam at this at 100, then the temperature begin to increase again until it reaches a 120 degree here. So now say we should calculate the total amount of energy needed to change that, to make that happen. So what we do is that we look at from this stage A, what the energy needed here. Since temperature change, so that means I will use Q is equal to mc delta T. M is the mass of the ice, C is the specific heat capacity of the ice, and delta T is temperature change. Temperature change here will be 30, that is 0 minus 30. That will give us let's look at the solution. So for stage A, or which I call part A, I have Q is equal to MICI delta T. I is telling us it is ice, just to indicate that what I'm working on now is ice. So the mass is 1 gram, but I need to convert it to kilogram. I need to convert it to, except if you are given the specific capacity in joule per kg per degree, per gram per degree, so you can leave it like that. But I converted it by divided it by 1,000. If I divide by 1,000, I have this value. That is 10 to the power minus 3, means divided by 1,000 times the specific heat capacity of ice, then times temperature change. I have 62.7. So let's go back to stage B. At stage B, you will see that temperature is not changed. The temperature is constant at 0. So that means there's a latent heat. The heat you supply here is latent, which you will use ML, M times L, M times latent heat of fusion of ice. So that's why I use Q is equal to ML. That I put F to show that it's for fusion. It's for fusion of ice. So this is the mass, and this is the specific heat capacity of fusion of ice. So if I multiply this, I will get 333 joules. Then part C, let's go to stage C. This is stage C. After all the ice has been converted to liquid water, the temperature begins to increase again. So when temperature increases, you use MC delta T, because temperature here I did not use MC delta T because temperature did not increase. It is ML I will use. But here temperature increases from 0 to 100. So change in temperature is 100. That is 100 minus 0. 0 is the initial, 100 is final. So mass is still the same mass. Then C is now specific heat capacity of water, because it has turned to water now. You will not use specific heat capacity of ice again. So let's go. So that's why I use Q is equal to MC delta T. W is telling you is now water. That's why I put WW to show that it's for water, not for ice again. No. So this is the mass. This is the specific heat capacity of water times the temperature change. So I will get a 419 joule. Then part D. So here all the waters are the what's it called? The temperature has increased to 100 degrees Celsius. Then the water we want to change to another form, that is to a gaseous form. So we are supplying it, the temperature did not change. That means you still use ML as stage D. Because you are supplying heat, temperature did not change. It means the heat you are supplying is latent heat of vaporization, because the water will begin to turn to vapor. So we use ML again, and ML is for vaporization. That's why I put V, that's stage D. So this is the mass, this is the specific heat, latent heat of vaporization of water. So if I multiply the two, I will have this value, 2.26 times 10 to the power 3 joules. So then the last part, after all the water has been converted to ice, you are still supplying it, then the temperature will begin to grow, begin to increase until 120. So change in temperature will be 120 here minus 100. That will give us 20. So because temperature change, I will still use Q is equal to MC delta T. MC delta T. So this is the mass. This is the specific heat capacity of steam times the temperature change, which is 20. So I have first 40.2 joules. SS that I use here is for steam, so that we know that it's for vapor. So the total amount of energy needed to take 1 gram of ice from -30 to steam at 120 degrees, the sum of all the 5 heat that you have calculated, heat energy you have calculated. If you sum them together, you have 3.11 times 10⁻³ joules. So another example, and I believe we are following. Please follow so that you can really understand it. Because it's 0.05 kg. Okay, I'm coming. Somebody is raising his hand. Let me know what's happening. Does it mean that you cannot hear me or what? Why are you raising your hand? Does it mean that you cannot hear or what? You can unmute yourself. You can unmute yourself.
Yes, good morning, sir.
Good
I
morning.
can hear you, sir, but I have a question based on the first example, sir. So before we go to the second example, please.
Let's go to the end of the lecture first, please.
All right, sir.
Okay, a 0.05 kg ingot of metal is heated to 200 degrees Celsius and then dropped into a light insulated beaker containing 0.400 kg of water initially at 20 degrees Celsius. That means the water is at 20 degrees Celsius initially, the first temperature of water. The final equilibrium temperature of the mixed system is 22.4 degrees Celsius. Find the specific heat capacity of metal, assuming the energy absorbed by the container is negligible. Take the specific heat capacity of water to be 186 joules per kg per degree Celsius. So this one, let's try and interpret the question. They have a metal, and the metal is heated to 200 degrees Celsius, very high temperature, and the mass of that ingot of metal is 0.05 kg. They now quickly transfer it to a beaker, and that beaker is containing water. The mass of water is this, and the water is at 20 degrees Celsius. They say the beaker is light and insulated, meaning that it cannot take any energy. So that's why I highlighted it with another ink to know that this statement is very important. They now say find this. Okay. The final equilibrium temperature of the mixed system is 22.4 degrees Celsius. Find the specific capacity. So what we do now is that, as I've said before, that the heat energy lost by the hot object or hot materials is the heat energy absorbed by the cold body. So that's what we use. The hot body now is the metal, while the cold body now is the water. We will not include the container because they say the container is light. If they say light, that means the mass is negligible. So you can ignore the heat absorbed. No matter how the thing we absorb it, but it's negligible. That's why they put light. So assuming the energy absorbed by the container is negligible, they put it there. So let's do that. So okay, recall that Q code is equal to minus Q what? But we assume that the system is sealed and some of the water that may vaporize when the ingot is dropped cannot escape. So if you have a beaker, an open beaker, and you drop that object, you drop a metal that's the temperature is as high as 200, you know that the water will vaporize and film or vapor will come out. But we assume that such did not happen. That's why I say we assume that the system is sealed and some of the water that may vaporize when the ingot is dropped cannot escape. So water vaporizes, but it cannot escape. It's still within that system. Since the container is light and insulated, it means the mass and heat absorbed by the container is negligible. So we use this, heat energy absorbed by the colder body is equal to minus heat energy supplied by the hot body. So my cold body now is the water. My hot body now is the metal, the ingot of metal. So I still use change the temperature is Tf minus Ti. So the mass of water given, you put it here. The specific heat capacity of water, you put it. Temperature change is, I think, is from 22.4 minus 20. That's like 2.4 or so. So for that of ingot of metal, that would be 20 the final, I mean 22.4 the final minus 200 degrees Celsius. So I just cross multiply because I want to find the specific capacity of that metal, which is Cm dc. So I will divide both sides by minus m bracket Tf minus Ti. So if I divide it, I will have what I have here. So I begin to supply the parameters given. Mass of water is 0.40. The specific capacity of water is 4186. Then temperature changes, I've said before, is 22.4 minus 20. So the mass of the ingot of metal is 0.05 here. Then temperature change is 2.24 minus 200 degrees Celsius. So if you do your mathematics, you just subtract this, multiply by this, and divide by what you have as denominator. You have this, then this, and your Cm, that is the specific capacity of that object, will be 452.5 joule per kg per Kelvin. So which can convert to standard form. I write it in this form: 4.53 times 10 to the power 2 joule per Kelvin per kg per Kelvin. So that is that about that example. I believe you understand. So you can reserve your question to the end of the class so that we don't waste most of the time. Then, what mass of steam initially at 130 degrees Celsius is needed to warm 200 kg of water? To warm 200 kg of water in a 100.0 gram glass container from 20 degree to 50 degree. They say what mass of steam that was initially at sorry, I can't say this again. Okay, that was initially at where is it now? At 130 degrees Celsius is needed to warm 200.0 gram of water in a 100.0 gram glass container from 20 degrees Celsius to 50 degrees Celsius. So this is the final temperature. We see that the hot body they use here is water, and it's at 120 degrees Celsius. It's higher than the what's it called? That the what's it called now? Point of water, the steam point, yeah. So the water will change to steam at 100. So this 130 is higher. Definitely before the temperature will move from 130 to 50, some phase change will occur. Because when you drop it in the water, the temperature of the higher body now, which is water, will begin to drop until 100. When it gets to 100, so the steam will change to liquid water at 100 until, and after that, it will start, the temperature will start decreasing up to 50 degrees. So these parameters have been given. So the latent heat of fusion of ice, the latent heat fusion of latent heat of vaporization of water, the specific heat capacity of ice, specific heat capacity of water, the specific heat capacity of steam, and the specific heat capacity of metal, because these are all what we need to do the question. So we still use this our simple relation, that is law of conservation of energy. So in this case, the gaseous water, that is the steam, which is the hot body, undergoes 3 processes, or is it 3 or 2? It's 2 or 3. The steam, the temperature drops first, then the steam change to water, then the temperature, that's 3 stages. Yeah, that's 3 stages. So a decrease in temperature from 130 degrees Celsius to 100, that's the first thing when you added it to that cold water. this thing will happen. The temperature at 130 degrees will drop to 100 degrees Celsius. Then at 100, condensation will take place. That is the gaseous water will change to liquid water. And that's at 100. Then the last stage is that after all the gaseous water has been converted to liquid water, decrease in temperature begin to happen from 100 until that final temperature. So we have to calculate energy needed in all these three stages. So from here, the first stage I will use MC theta because temperature change. So second stage I will use ML because temperature did not change. All the condensation takes place at 100 degrees Celsius. Then lastly, the last stage I will use MC delta T. So I think this is clear enough. Then Q1, that's MC delta T. That's 100 minus 130 will give us this. This is the mass of the steam. This is specific heat capacity of steam. Just put this there. You have this, and the heat needed in the first stage is 6.03 times 10 to the power 4. This is 10 to the power 4. This is the mass because we want to determine the mass of that steam needed. That's ms joules. So second stage, I will use ml as I've told us before, that because temperature does not change, it is latent heat that will supply at that point where condensation is taking place. So I'll use ml. ml. M is the mass of the steam. L is the latent heat of vaporization of ice. So this is the mass, and this is the latent heat of vaporization of ice. This times 10 to the power 6, 2.26 times 10 to the power 6. If I multiply the two, I'll have 2.26 times 10 to the power 6 times mass of that steam joules. Then the third stage, so I will use because temperature change, I will use MC delta T. Change in temperature is 50 minus 100. So I will supply the specific heat capacity. But this should not be S. This should be for water, because the thing has changed from gaseous water to liquid water. Now the temperature is dropping. Please take note of that. So this is specific heat capacity of water. So that's why I put 419 times 10 to the power 3. This is specific heat capacity of water. You put it, you have this value for the heat energy needed at stage 3 for the steam. Then we are done with the steam. The total energy needed for the steam to change from temperature of 130 to 50 is the addition of all the three. So that's why I say Q hot is equal to the first one plus the second one plus the third one. So it will give me this. So the next thing is to consider the heat absorbed by water and the container. So I say the water and the container undergo only one process, that is an increase in temperature from 20. Their temperature was 20 degrees Celsius, and the final temperature is 50. That means it's just a change in temperature they undergo. For water, I'll just use MC delta T. That's for water. Then for container, we use MC delta T again, what temperature change, and we had it to. That's the energy absorbed by the cold bodies. We have cold bodies now, water and the container. So the amount of energy transferred in this process is Q code, which is MC delta T for water plus MC delta T for the container. So it supply the parameters given. I have 0.2 as the mass of the water, then 4.19 times 10 to the power 3 as the specific heat capacity of water. The temperature change, that's final minus initial, plus that of a container. I will do this, and the one at the left, which is this and this, and I'll add it together. If I add it together, I'll get 2.77 times 10 to the power 4. This is 10 to the power 4. Sorry for that error that is saying 1 instead of 10 to the power 4 joules. So now we now use a law of conservation of energy. That energy absorbed by the cold body is equal to energy minus energy supplied by the hot body. So this energy absorbed by the cold body, 2.77 times 10 to the power 4, is equal to minus. This minus is this. Then this is what we got when we do with the steam. We check this place. Yeah, this is it here, minus 2.53 times 10 to the power 6. So that's why I put it here. So you can now find this mass of the steam here. So by dividing both sides by 2.53 times 10 to the power 6, you have 1.09 times 10 to the power minus 2 kg. So I can multiply by 1,000 so that I convert to gram. So I have a 10.9 gram as the mass of the steel that is used. So let's quickly look at this example. I think we have like 2 or so more. So in an X-ray tube, 10 raised to power 18 electrons per second arrives with a speed of 2 times 10 to the power 6 meters per second at a metal target of mass 0.2 kg. And so each capacity 500 joule per kg per Kelvin. If the mass of an electron is this, that's 9.0 times 10 to the power minus 31 kg, and assuming that 98% of the incident energy is converted into it, then find how long the target will take to rise in temperature by 50 degrees Celsius, assuming no heat loss. So let's try and analyze this question. They say in a tube, which is an X-ray tube, we have 10 to the power 18 electron that's arriving at a particular metal target with this speed. And the mass of the metal target is this. So each capacity of the metal target is this. The mass of an electron is this one. Now say all the energy the electron carried to the metal target, let's assume that is 98% of that energy that is converted into heat. Find how long the target will take to rise the temperature by 50 degrees Celsius, assuming no heat is lost. Yes. So electron that's moving an electron moving an X-ray tube has a kinetic energy. So it means it is the kinetic energy of the electron that is converted into heat energy. So that's the approach we are using. So the kinetic energy of an object, just one object, is half mv squared. This is an elementary formula. Half mv squared is the kinetic energy of any object. So the kinetic energy of an electron arriving at the target in 1 second, just one electron, will be half m. Now this 9.1 times 10 to the power minus 31. That's mass of one electron times the speed square, half mv squared. This for electron that's the arriving target in a second. But say it's 10 times 10 to the power 18 electrons are arriving at the target in that 1 second. So let's find the total kinetic energy of all the electrons arriving at the target in a second. So I've gotten this is kinetic energy of one electron arriving the target in a second. So if I multiply this one for one electron times 10 to the power 18, it will give me the total kinetic energy of all the electrons arriving the target per second. This is total kinetic energy. So it will be 1.82 joules. So I believe we understand that. So I calculate the kinetic energy of one electron, then I multiply by the number of electrons to get the total kinetic energy of all the electrons arriving the target at 1 second. In 1 second. So, but we don't know how many times the electrons use before they stop. So let's say the time is t. Though we know that of 1 second to be 1.8 t. But let's say the electron hits the target for 5 minutes. So we just multiply by 5 minutes to know the total kinetic energy in that 5 minutes. But now we don't know that time. That's why I put t. In time t, the total kinetic energy of all the electrons arriving at target will be Ke is equal to 1.82. That's that kinetic energy of all the electrons arriving at target in 1 second. Times t, that's that time that we don't know. This is all the total kinetic energy of all the electrons arriving at the target as time t that we don't know yet. But the question says, remember that 98% of this energy that we just calculated now is converted to heat. Let's calculate the 98% of this energy. That's 98 over 100 times 1.82 t. I didn't put t here, but t should be there. So That means I have 1.8 T. So this is the amount of energy, amount of kinetic energy that's converted into it before the temperature of the metal target rises to what? To what they call it, to 50 degrees. So this is now what you use at the heat. You now say 1.8 T is equal to MC delta T. MC delta T is the energy absorbed by the metal before its temperature rises to 50, or rises by 50 degrees Celsius, rather, rises by 50. So I've just equate the two. I'm giving this to be 0.2. I'm giving C, maybe its capacity of that metal target to be 500, then times delta T. That is 50, multiply it, then divided by 1.8 to get that T. So I have 5,000 divided by 1.8 is 277.7, which is approximately 278 seconds. If I divide this by 60, so I will have 46.3 minutes. So this is the time we are asked to calculate in the question. They say, find how long the target, that is metal target, will take before its temperature will rise by 50 degrees Celsius. So it will take that target for 3 minutes before its temperature can be rise to by 50 degrees Celsius. So that is that. I believe we understand that. Let's do this before. I think this is the last one. Yeah, this is the last one. So let's quickly look at this. Look through the assignments before I allow questions. So water flows. That's another question. I think this should be number 4 instead of number 2. Sorry. Water flows at the rate of this people. You are disturbing me. It's blocking my. Don't raise your hand. Let's wait. Reserve your question to the end. I've said that many times. Please. Water flow at the rate of 0.150 kg per minute through a tube, and is heated by heater dissipating 25.2 watts. That's power dissipating by that heater. The inflow and the outflow water temperature are 15.2 degrees Celsius and 17.4 degrees. That is, when water is entering that tube, the temperature is 15.2. But when by the time water is leaving, the temperature has become 17.4. So the difference temperature will be this value minus this value. When the rate of flow is increased to 0.2318 kg per minute, and the rate of heating is increased to 37.8 watts, the inflow and outflow temperature remain unchanged. Find the specific capacity of water and the rate of loss of heat from the tube. Now they find the rate of loss of it. That means you don't assume that no energy is lost to the surrounding. You don't assume that assumption. You don't do that assumption. Yeah. So what I will do now? So look at the mass they give me. If I use what is supplying the energy now is the heater. So energy supplied or power supplied by the heater is the power absorbed by the by the water, or let me say energy supplied by the heater per second is equal to energy absorbed by the water per second. That's what we use. So record that power is equal to energy per time. So that was the energy supply, supplied by the heater per second. That's divided by time. It's equal to energy absorbed by the water per time. So rate of energy supplied by the heater is equal to rate of energy absorbed by the water plus some of the power, some of the heat that is lost during the process. So take note, this is what we are using. I told you that is the heater that supply the energy per time. Then that energy per time is absorbed by the water. plus some amount that is lost, because they ask us to calculate heat loss. So we cannot assume that we cannot say assume that no heat is lost to surrounding. Here they say heat is lost to surrounding. So you have to take note. That's why I say plus that small amount that's lost to surrounding. So I will just use the power. This is P is equal to MC delta T. This energy absorbed by the water per unit time plus the energy per unit time. Don't forget that energy per unit time is power. So that I can say power, I can say energy per unit time. So I'm still saying the same thing. So plus the one that's lost to the surrounding. So in the first case, this formula we use for the two. But the first case, you see that they give us power to be 25, where is it? 25.2. And the mass of the water per minute is 0.15 kg per minute. So that's why I use the 25.2 and 0.15 kg per minute. So I have to divide it by 60 to get per second. So times specific heat capacity of water times temperature change plus the HL, the one that is lost to the surrounding. That's for first case. For the second case, they say the power is increased to 37.8 and the rate of water increased to 0.2318 per minute, kg per minute. So I still divide it by 60 to get it in per second. Because this is power, this cannot be just ordinary mass. It will be ordinary, it will be mass divided by time, so that this also will be in power. So times C is the specific capacity of water, because still the same water, C here. So times temperature change. They say the temperature remain the same. The inflow and outflow temperature remain the same. That's why the change in temperature in the two will be the same, plus the same heat lost here. So this is like a simultaneous equation for us to solve. So divide this by this. You have this 0.025 times C times temperature change plus HL is equal to the power supply, that is 25.2 power supply by the heater. So that's the first one. So the second one, if you divide the 0.2318 by 60, you have what you have here times C and times change temperature plus the HL, the last one, is equal to the power supply. So this 7.8 is what I brought to the right. At 25.2, I brought to the right, so that it will look exactly like a simultaneous equation. So these are the equation. I just multiply 0.025 by this. I will have 0.055C plus HL is equal to 25.2. And this one also, I'll just solve this equation simultaneously. I'll solve the last two equations simultaneously. Solve equation 3 and 4 simultaneously. Subtracting equation 3 from equation 4. So because I have HL here, I have HL here, I can just use the elimination method. I just subtract one of the equation from the other, so that I can eliminate HL. So I have 0.03 C is equal to 12.6. If you subtract this guy from this guy, you get what you have there. You subtract 25.2 minus this one, you have 12.6. Then divide both sides by 0.030. So you have C is equal to 12.6 over 0.030, which will give you 4.200 joule. This is the specific heat capacity of water you are asked to calculate. So I just convert it to write. I just write it in standard form. That's why I have this joule per Kelvin, per kg, per Kelvin. So in order to get the heat loss, now use one of the equations and put the value of C you have gotten there. You can use equation 3 or equation 4, anyone you use. You can use anyone here, but this will be easier. You can use any one of these two to get. I think in my own, I've used the equation 3, the first one. So I just put the equation 3. This is equation 3. So the value of C that I got, that 4200, I'll just put it here. 0.055 times 4200. That's why I have this guy plus HL that I want to find is coordinate. Then I make HL the subject. I brought this one to this side, so my HL will be 2.1 watt. So this is the heat loss for the surroundings. So during the process, so you have one assignment here exactly like the the one I gave you before. In an X-ray tube, 10⁻80 electron per second arrive with a speed of 6 meters per second at a metal target of mass 3.2 kg and specific capacity of 500. The same thing. If the mass of an electron is this 9.0 times 10⁻³ 31 kg, and assuming that 96.5% of the incident energy is converted into heat, find how long the target will take to rise its temperature by 50 degrees, assuming there is 7.5 heat loss. So the second one, what would be the final temperature of 200 grams of hot water at 8 degrees Celsius mixed with 100 grams of ice when just half? This should be half, not half. So half of the ice as melted. So the capacity of water is this, and the latent heat of fusion of ice is this. So the amount of heat energy required. Okay, let me change that to half. It should be half. Okay, sorry for that. So it should be half of the ice has been melted. So the last one, the amount of heat energy required to raise the temperature of a material by 10 degrees Celsius is this. What is the heat capacity of the metal? This is a very simple question. So the next thing now is what we have in the next class. So a gas kept at a very, okay, we have the topic is a macroscopic description of an ideal gas. Microscopic description of an ideal gas. So ideal gas. So let's look at the meaning of an ideal gas. A gas kept at a very low pressure, that is a low density gas, is what is called an ideal gas. A gas at a very low pressure. Oh, I think in our lecture 2, I gave you a figure whereby I begin to reduce the pressure of some gases. And I told you that at a point, the temperature of the gases agree well together because they begin to assume the nature of an ideal gas. So it's that means a gas kept at a very low pressure would behave exactly as an ideal gas. We call them an ideal gas. So for an ideal gas, PV over NT is always a constant. That's R, that we know, the molar gas constant. At all pressures, this PV over NT is always a constant. So the equation that relates the state variables, what are the state variables? We have the volume, that is, you know the meaning of state. When they say it's in gaseous state, that's why they call it state variables. The variables that define the state of a substance or of a system was called state variables, and they are volume, temperature, pressure. So then I said the equation that relates the state variables is known as the equation of state. This equation is very, very complicated, but simple for ideal gas. That is for gas that's maintained at a very low pressure. It's very simple. That's why you can work with it. Yeah, it's very simple. You understand, yeah, because it is for ideal gas. If the gas is not ideal, the equation is more complicated than what you see. Suppose an ideal gas is confined in a cylindrical container whose volume can be varied by means of moving piston. So this is the cylindrical container, which volume can be varied by moving piston. This is what's called piston. I can press it down. So if I press it down, the gas will be reduced, let's say, or I can move it up so that the gas volume will increase. So that's what we are saying. Let's say this is the original position of the piston. When you release the piston and the piston moves up, the gas will move up too, filling more volume than before. That means the volume has increased. So the change in volume is equal to the area of the piston times the change in the height or in the length, which I call delta H. So you know volume is always area times height, that is base area times the height by which the piston has moved. So macroscopic diffusion of an ideal gas. Experiments have shown that for such a gas, For such a system, when the gas is kept at a constant temperature, its pressure is inversely proportional to its volume. We all know that right from our secondary school, that at a constant temperature, the pressure of the gas is inversely proportional to its volume, or the volume of the gas is inversely proportional to its pressure. That's called nothing but Boyle's law. That is, P is proportional to 1 over V. So this is Boyle's law that many of us know right from our elementary level. So when the pressure of a gas is kept constant, its volume is directly proportional to temperature. That is, when you keep the pressure of a gas constant, that is, you do not allow the pressure to change. So as you are increasing the temperature, the volume also will be increased. So as you are reducing the temperature, the volume also will be reducing. So that is what's called a Charles law. So which stated at a constant pressure, the volume of a gas is directly proportional to its temperature. That is, V is proportional to T. These two observations, that is Boyle's law and Charles law, are summarized by an equation of state for an ideal gas, so which is called a general gas equation, where R is a constant called gas constant, molar gas constant, and N, small n, is mass over molar mass. You see the fact that small n is the number of molecules divided by Avogadro constant, and Kb is what is called a Boltzmann constant. So it's equal to R divided by Na. You know, this is my small n. If I put capital N over Na, it will be PV n capital N RT over Na. So that I can have R over Na to be Kb. If I do that, so I will have a PV is equal to N KBT. So this is another way to write a equation of an ideal gas. That is ideal gas law. So ideal gas law. So this equation, any one of them can be called an ideal gas law, which you can see call it a general gas equation. So we continue this in our next class by God's grace. God's grace. So next class will be like a revision where we interact on what we have learned so far, or our experience in let's say University of Ibadan at large. So on another thing, and so there may be a short test that day. There will be a short test. That's it. Just prepare, read your note, and get ready. So thank you, everyone. So let me unmute you guys for you to ask your questions. So you can unmute yourself now and ask your question one after the other.
Good morning, sir.
Good morning. Good morning. How are you?
My name is Falade Esther.
Good morning, sir.
Okay, Falade, how are you?
My question is this. First, you didn't give an example based on the integral formula, sir, so that it can be a bit clearer. Now we can use the formula. Secondly, sir. If we read through the notes, because a majority of the examples were not clear, so I plan reading it again over and over again. If we have any questions, how can we get across to you, sir?
This is a university. So majorly when you enter, when you come in physically now, so there will be many tutorials. You don't direct questions to your lecturer, because there are first reasons that there are many things on the table for them to lay their hand on. So after you, another set, they will take another level, they will assess, they will do everything. That's why in the university you see many tutorials. Even physics department, I think Faculty of Science at large, there's a tutorial for 100 level and 200 level by senior colleagues too. I mean by your seniors. So that the tutorial. No, if the lecturer is less busy and you ask a short question that can quickly answer you, can do that. During the class, he will be glad to answer you. But after the class, he may not have that time. He may have, like me. I've answered many students in the past, many of them. But I'm getting more busier every day. So So let me say something about the first question. About the first question. I will just explain so you can. What they will do here, listen though. What they will do here is that I can give you just an example here now. So they will give you the mass of that body. They will give you this C. They may give you in terms of T. For example, they can say C is equal to maybe 5/2 T square. Are you listening? 5/2 T square plus 3T minus, they can say minus 5. Then find the heat energy that will supply. So you need to integrate. I believe you did integration in secondary school.
No, sir.
So that's the issue. That's the issue. But you'll be doing it when you enter university. What department are you in?
Pharmacy, sir.
Oh, pharmacy. Yeah, I think you will do it in physics. Probably physics 101. Yeah, physics 101 will guide you. But if you want to integrate, it's very simple. Let's say I want to integrate 5T. For example, I want to integrate 5T. So what I will do, I will look at the, let's say 5T square. I will add 1 to the power. Listen, I will add 1 to the power. The power is 2. 5T square. The power is 2. If I want to integrate with respect to T, I will add 1 to the power. Whatever I get as the power, I will now divide it. I will now divide everything by that number. You know, I say 5T square. So I will add 1 to it. I will get that's 5T raised to 3. I will now divide everything by that 3. So I've integrated. I will now add constant of integration. So that's integration. That's integration. But this one is what is called definite integral. Definite is then that they give you the lower limit to be initial temperature and the upper temperature. So what you will do that whatever you have gotten after you have integrated, you now supply the upper. This TF can be maybe 20, and this one will be maybe 10. Whenever you see that T, you supply whatever you have here. Minus, you supply the lower limit also. When you enter physical class, I will still explain that more. Don't let us waste time on this. We still resume. When we resume physical class, we explain better. Okay. All right. Another question. Have I answered you?
Yes, sir. Thank you very much.
If you have another class, you can send a question to me. But if I have time, I can answer you. But I may not have that time. But you can send it, maybe if I'm less busy, I can just get back to you and say, "Oh, this is what you are asking." I've done that in the past for many students. Okay, I'm listening. Yeah.
Good
morning. Your question. Okay. I cannot hear. Speak up now.
I have a question for an example.
Okay.
One that has to do with the mass of a steam initially at 130 degrees.
Okay.
We have another class now.
Okay, this one, Abby. Okay, ask your question because you have another class now.
Okay, sir. Now, why is the mass?
Why is what? I cannot hear. Hello, send the question to me. I will answer that student.
Hello, good morning.
Hello. So let's call it a day. They are having another class using the same Zoom link now. Might have been keep some people waiting. So let's reserve our question to next week. So next week will be for question, interaction, and others. So thank you, everybody. Thank you. We'll meet next week by God's grace.
So please, could you put the slides on LMS?
It's already there. I will still.
Okay, thanks.